Guys, today we're going to talk about power. This is building on what we learned last time, which was about work and energy, and power grows right out of this. So the question of what power is, well, power is the rate at which work is done. So power is not energy, power is not work, it's how fast we do the work. So for example, if you're trying to pump the water out of a swimming pool, you get an electric motor and you put it on your pump and you start pumping the water. But if you want to do, and you're doing work lifting that water out of the pool. But if you want to do the job faster, you have to go get a more powerful pump, a pump that can do the same work in less time. So we have a formula for power, and here it is. Power is work divided by time. And as you remember, the units of work is joules, and the units of time is seconds. So power is measured in joules per second. And for shorthand, we call that watts, which you've probably heard of before. Watt is the unit of power in physics. So for example, a 100-watt light bulb releases 100 joules of energy into the room every second, 100 joules per second in the form of light or heat or some combination like that. A 1,000-watt hair dryer or a 1,000-watt microwave oven heats things up at the rate of 1,000 joules per second, 1,000 watts. Okay, the math on this is not particularly difficult. So suppose we release 60,000 joules of energy in 10 seconds. How much power do we produce? Well, it's going to be 60,000 joules divided by 10 seconds. We're going to get 6,000 watts. That's the power output. If we do a job like lifting a 20-kilogram mass, which would be 200 newtons, and we lift it up 4 meters, sort of like I was lifting the bowling ball in class last time. We're raising 200 newtons to an altitude of 4 meters, and we do it in 4 seconds. What's our power output? Well, the 200 newtons times 4 meters, that's the work we do, which would be 800 joules, and we divide that by the 4 seconds, and we get 200 watts. So 200 watts for lifting 20 kilograms up 4 meters in 4 seconds. That would be a project. So that's might put it in perspective of how much energy a 100-watt light bulb actually produces. Okay, let's do a couple more here. We've got Atlas and Hercules, and they each lift a 200 kilogram barbell 2 meters off the ground. So they're just doing a dead lift, picking it up off the ground, putting it over their head. 200 kilograms, 2 meters off the ground. Atlas lifts his in 1 second. Hercules lifts his in 3 seconds. First question is, who does more work? And I would like you to pause the video at this time to figure that out. Who does more work? Okay, 3, 2, 1. Here we go. They do the same amount of work because they both raise 200 kilograms, 2 meters. If we convert the 200 kilograms to newtons, that's going to be 2,000 newtons times 2 meters would be 4,000 joules of energy for each of them, 4,000 joules of work that each of them do. Second question is, who is more powerful? In other words, who produces more power while lifting this weight? And I think you can see fairly quickly that Atlas is more powerful because he does all that work in only 1 second, while Hercules takes 3 seconds. So if you can do the numbers here, but you'll find that the power that Atlas produces is a number 3 times as big as the number that power that Hercules produces. Okay, we're going to take a quick review here of the work energy theorem, which says that the mechanical energy in a system is equal to the work done on that system. And we have all the formulas that we learned last time here. Okay, so basically, if you do work on a system, like lifting a bowling ball over your teacher's head, the potential energy that that ball has after it's been lifted is the same number of joules as the number of joules of work that was done. And then likewise, if we drop the bowling ball, we saw that we would have the same number of joules of kinetic energy when the ball reaches the floor because it's going as fast as it can go just before it reaches the floor. So work energy theorem says that the work done is potential energy or the kinetic energy that the object has that we've done our work on. Why are we reviewing this? Well, we're going to think about what data do we need to calculate the work going upstairs. So if we go upstairs, we're doing some work. We're technically doing the work on ourselves because we're lifting ourselves up to a higher level. So we want to know what data do we need to collect to calculate the work that we do going upstairs, and also the power that is produced when we go upstairs. And I want you to pause the video for a moment and think about this for a moment. What information do we need? Okay, hint, we need three things. We need three pieces of information to calculate both the work and the power. Okay, and those pieces of information are the weight of yourself, because that's the force that you're exerting. We need the time that it takes to go up the stairs. We need that to calculate the power. And then we also need to know the distance that we go, the distance that we apply that force. Okay, so we need the distance, we need the weight, and we need the time that it takes. The weight and the time are very straightforward. The distance is a little tricky though. We need to think about this for a moment. So when we're measuring the distance that we travel, do we want to measure slant distance going up the stairs, or the vertical distance that we went up the stairs? Or maybe even just the horizontal distance and ignore the vertical? So which do we need? Do we need the vertical distance, the horizontal distance, or the straight line slope distance? So think about that for a moment, make a prediction. And now I'm going to give you a hint, which hopefully will lead you to the answer. So here we go to a hint. So pause it if you're still thinking. And here we go. Okay, think about the work that we do when we go up the slope. We do work, and when we get to the top of the stairs, we have potential energy. And the amount of potential energy that we have has to be equal to the amount of work that we did. Now, how do we calculate our potential energy? Well, we look at the altitude that we've gained. If we've climbed up 3 meters, then we plug 3 meters into our formula for potential energy for the height. And it doesn't matter what our slope distance was. Like if these were fairly shallow steps, we went like 20 meters to climb 3 meters, we've only gained 3 meters worth of potential energy because the altitude, the elevation gain is only 3 meters. So the information we need for the last question is the elevation gain, not the straight line gain, not the horizontal distance, but the vertical altitude that we've gained in climbing the stairs. Okay, because the potential energy we have at the top is equal to the work that we did going up the stairs. And the potential energy is determined by how high we have climbed. Okay, you're going to do a mini lab. You're going to do it in virtual form. Normally we would do this in live. We all run up the stairs or up the bleachers at school, but we can't do that obviously because we're out of school, but it's going to take too long for us to come back. So we're going to do this in a virtual mode. The purpose of this lab is to apply the equations for work and power and to compare how we perceive work and power when we are the ones doing the work and producing the power. Okay, so let's get out take a quick look at the worksheet here. Okay, so this is it. This is attached to our assignment today. Read the information. It gives you the background on it about power and work. This procedure is if you were doing it yourself in class. Now read through it anyway, even though you're not doing this procedure, so you have some idea of what's happening on the next page. Because rather than having you gather data on yourself and collect data from classmates, I've provided this data for you. So Ron is going to stand in for you. So Ron has a mass of 85 kilograms, which works out to be a weight of 850 newtons. You need to remember or go back and figure out how you convert kilograms into newtons of weight. This staircase that these people are climbing is 8.5 meters high, and that is the vertical height. So we're talking probably three flights of stairs, 3 floors, going from the first floor to the third floor, to the fourth floor actually, but going up 8.5 meters. And then Ron runs it in 23 seconds. You are going to calculate the work that is done. And the way you calculate work is using the work equation, the force times the distance, and should come out to 72.25. You do all these calculations, okay? So you can be certain that you know how to do them. Then you calculate the watts, and the way you calculate the power is the work divided by the time. So the joules divided by seconds. Now, this bottom box here is, I want you to be careful with this. Once each person is at the top of the stairs, I want you to calculate the potential energy that they have as they're standing at the top of the stairs. And when you do that, I want you to use the potential energy equation, which is PE, potential energy, equals mgh, the mass times g times the height. I want you to actually write those numbers in here, or type them in if you're using your keyboard, to calculate the potential energy that they have. Now, if you understand the work energy theorem, you know that the potential energy is going to be the same as the work that was done. It's no coincidence that these are the same number here. But I don't want you to just copy the work into the lower box. I want you to have the practice of applying the potential energy equation. And I want you to give yourself a backup to make sure that you didn't make a mistake when you were calculating the work. So by doing it 2 different ways, we get to see that you know how to calculate potential energy, and you get to make sure that you didn't make an error. Okay, so you are calculating all the numbers for all these different people, all these different classmates at some other school, which is not Ledyard High School. Then there's a number of questions to ask. Now for these first 4, I want you to provide specific examples from the data table. So since everyone climbed the same flight of stairs, did they all do the same amount of work? Well, that's a yes or no question. But then I want you to give examples. I want you to compare the work that Ron did with the work that somebody else did. And either they're the same or they're different. But I need you to articulate that. I need you to pull the numbers out of the data table to back up your answer to the question, yes or no. Likewise, how did the speed affect the amount of work that they did? Would they have done more work if they ran up the stairs faster? That's really not a question that can be answered from the data table. That's something that you have to get into and think about and work out. But you can see, you can get examples to kind of spot the pattern in the data table. Finally, in this experiment, is it possible for a small person to do as much work as a bigger student? Why or why not? And again, show examples from the data table of the work that small people did versus large people did. And then finally, is it possible for a small person to produce as much power as a bigger student? And again, provide examples. If you say it's not, show that small people always produce less power. If you say, yes, it is possible, then you need to show an example of when a small person did produce more power. Next page is thinking about how we personally perceive work and power. That's what these questions are leading you towards, so think about these. Normally we would do this as a class discussion after the lab, but this is the best format we can do. So I want you to respond to all these questions, turn them in. You've got your own copy of this handout, so you can type your answers right on there. That is our assignment for today. All righty, have a great day, and we will see you next time.